All right, good evening and welcome, everyone. Thank you so much for joining us tonight, even though we have chosen to fight against state of origin once more. We keep choosing the wrong night for this event. We want to warmly welcome you to the Brain Cancer Group's 9th awareness raising event, held annually here at New South Wales Parliament House. We acknowledge the traditional owners of the land on which we are meeting tonight. We pay our respects to their elders past, present and emerging, and the elders from other communities who may be here tonight. We want to thank, firstly, our parliamentary host, the Member for Canterbury, the Honourable Sophie Kotsis, New South Wales Minister for Industrial Relations, Minister for Work, Health and Safety. Sophie hopefully will be joining us shortly. Sophie, we thank you for your ongoing support, inviting us to hold our inaugural event here at Parliament House in 2016, and for hosting all our subsequent events since. We are honoured and privileged to have Sophie remain a firm friend and supporter of the Brain Cancer Group. We also want to thank all the parliamentarians who have popped their heads in and remaining in the theatre with us tonight, who have been joining us on what we recognise as a very busy sitting day. In particular, we want to extend a warm welcome to Dr. Michael Holland, the Member for Bega, Parliamentary Secretary for Health and Regional Health, who will be up on the stage shortly delivering a welcome address. We want to acknowledge the Brain Tumour Alliance Australia, BTAA, represented this evening by a number of their committee members. BTAA and the Brain Cancer Group have forged a strong relationship, bringing multiple educational events to the brain cancer community in the last few years. And also this August, TBCG will once again sponsor BTAA's Patient Forum, which will take place at the beginning of the annual Cogno Scientific Conference in Adelaide this year. Finally, we also extend our warm welcome to all our guests here tonight, our distinguished guests, our ambassadors, patients, families, carers, donors, sponsors and supporters, and business and community leaders and representatives of all other brain cancer organisations. Ordinarily, I would ask and invite Sophie to come up to the stage, but I don't believe Sophie is here still, so I will now ask Dr. Michael Holland to come on stage and deliver his welcome address.
Thank you, everyone. It's really a great honour to be here tonight. And I do represent Minister Sophie Kotsis, who is very busy, as you appreciate. She tells me she will be here at some stage this evening. I get these gigs because, as you heard in the introduction, I have that doctor in front of my name. I graduated 45 years ago and then went on to become an obstetrician and gynaecologist, but the last baby I delivered was about 4 years ago. I think I get the gig because my standard joke is we speak the same language. You don't need translators or subtitles. I understand what's going on here tonight. I also want to acknowledge the traditional owners of the lands that we're gathered on here, the Gadigal people of the Eora Nation, and extend that acknowledgement to any Aboriginal or Torres Strait Islander people here. I also want to acknowledge the traditional owners of the lands that we've all come from. I represent the Bega electorate on the far south coast of New South Wales, which contains several tribes of the Yuin Nation. And welcome to the New South Wales Parliament, the oldest parliament in Australia. I've met people here before at the previous events. It's always great to be back. I also want to acknowledge my parliamentary colleagues who have been here and some who have already left, but the member I see in front of me, the member for Albury, Justin Clancy, thank you for being here. And, you know, these events are advocacy events. People do come and go in these events, but the job is really to spread the message that we have surrounding brain cancer in our community. It's great to have, there's many parliamentary friends groups in Parliament, too many to name, but they have the same sort of function where we invite guests in to speak and provide advocacy on many topics, but particularly health. I want to provide a specific welcome to our distinguished guest speakers tonight, Professor Nick Pavlakis, Professor of Medicine at the University of Sydney and Senior Staff Specialist in Medical Oncology at Royal North Shore Hospital, who will be speaking on the precision generation learning lessons from lung cancer, and also Associate Professor Kimberley Alexander, Director of Brain Cancer Research at Chris O'Brien Lifehouse and co-lead of the Sydney Brain Tumour Bank, who will be speaking on Beyond the Scan, the Sydney Brain Tumour Bank and the promise of liquid biopsy. The expertise and vision that drives the conversations here will help shape the future of care and support for those affected by brain cancer. And I also want to acknowledge the representatives from the Brain Cancer Group here tonight, Associate Professor Michael Back, Director of Radiation Oncology at Northern Sydney Cancer Centre, Royal North Shore Hospital, who's also a VMO at the Central Coast Cancer Centre, Gosford Hospital, and the Sydney Brain Tumour Clinic, Genesis Cancer Care, and Associate Professor Adrian Lee, our great MC, who's Staff Specialist at Royal North Shore Hospital and Medical Oncologist. Also, of course, the board and members of the Brain Cancer Group, whose leadership and dedication make a night like tonight possible. As you know, this group was founded in 2000 by the eminent neurologist Dr. Raymond Cook and Dr. Michael Biggs on the Royal North Shore Hospital campus. And the Brain Cancer Group has built a remarkable legacy across its three pillars: research, education and support for patients and carers. Its work has touched countless lives, advancing treatment and providing much needed help for families and communities across our region. This year's theme, Learning from Lung Cancer, New Frontiers in Brain Cancer Research, Detection and Treatment, is an important and timely conversation as lung cancer research has made major progress in areas such as precision medicine, early detection and targeted treatment. And tonight we'll be asking what sort of lessons we can learn from that that can be applied to brain cancer care. As I said, I was talking to a couple outside whose daughter has experienced brain cancer and mentioned that 45 years ago I graduated. And in my career as an obstetrician and gynaecologist, particularly in gynaecology, there were women who were affected by infertility. And during my career, I would say to them, well, look, you have a condition called unexplained infertility, but that's only called unexplained infertility now because we don't know the answer of what the cause is. And that's what medical research is about, whether that applies to fertility or cancer treatment, is that research gives us the answers. So I've seen conditions go from being unexplained, untreatable, incurable, and over that time to see such major progress. And I've often referred to what I call my penicillin experience, living through a generation where something has really affected the survival, and that is in gynaecology, the acknowledgement of human papillomavirus as being the cause of cervical cancer, and now to be something that is basically preventable by immunisation. So this is the way people help in medical research. But we have to remember what we're here for as particularly the clinicians and researchers. It's about those people that we care for. Medicine's a compassionate profession, and we should never lose sight of those people who are the primary reason for us to be practicing. And that includes the patients, their carers, their families who are here, and your continued courage and advocacy in this field allows us to continue this advocacy and work. They inspire us, they give some urgency and direction to the efforts. I also want to acknowledge the various associations that were present in terms of supporters, the research institutes, medical institutes that are around, the universities, the hospitals, the laboratories, the medical imaging groups who help this brain cancer group, as well, of course, the wonderful philanthropists that keep work like this going. So thank you for being part of this tonight. I hope it brings some new connections, inspiration, and these events really raise inspiration for us in Parliament and across the community. So thank you.
Thank you very much, Dr. Holland. All right, now it's time to introduce our speakers tonight. And firstly, though, of course, tonight's theme is a little left field. We are literally going to hear about another cancer type within this Brain Cancer Forum. This may seem strange at first, but it wasn't too long ago that lung cancer diagnosis was viewed as dimly as brain cancers tend to be. Yet tonight we will hear from Professor Nick Pavlakis that lung cancer has gone through many different technologies, trials and research in recent years, successfully converting a poor situation into a much brighter journey for lots of lung cancer patients. On the back of this, we will hear from our second speaker, Professor Kim Alexander, who will shed light on how some of these learnings from lung cancer are being realised in brain cancer research. Together, we hope that we can also transform the brain cancer journey into a brighter path for future patients and their families. It is now my great honour to introduce Professor Nick Pavlakis to the stage. Prof. Pavlakis is Professor of Medicine, University of Sydney, Senior Medical Oncologist at Royal North Shore Hospital, and co-chair of our laboratory, Bill Walsh Translational Cancer Research Lab. He's also been past president of the Thoracic Oncology Group of Australasia and Clinical Oncology Society of Australia. Perhaps lesser known facts about Nick. His PhD was supervised by our very own Dr. Helen Wheeler, who unfortunately can't join us tonight. In addition, Nick used to cover Helen's brain cancer practice in the early days when Temodol or temozolomide was just coming through on the market. More importantly for me, it's my first time to introduce you to the stage. Whilst most of you know Helen has been my mentor for a very, very long time, I can truly say I would not be here tonight as a medical oncologist if it wasn't for the fact that I worked with you on a weekend ward round in 2009. Please welcome to the stage Professor Nick Pavlakis, who will lead our forum tonight on learnings from lung cancer, new frontiers in brain cancer research, detection and treatment.
Thanks for that kind introduction, Adrian. And I was going to tell the audience that I actually did treat brain cancers for some time in my early part of the career. And it's a real privilege, and thank you for asking me to be a part of this. I see some friends here, some colleagues, family, obviously of patients and carers and people with lived experience. And one of the things you mentioned is so true, Adrian, and I'll give you a little bit of a snapshot of what's happened in lung cancer. Lung cancer prognosis was actually worse than brain cancer when I first started. And I'll give you a little bit of a story of how it's evolved over that time. These are my disclosures. So in terms of epidemiology, lung cancer is actually the commonest cancer worldwide and the leading cause of cancer-related death still. In Australia, the figures are worldwide, but also within Australia. In terms of incidence, it's the 5th most common cancer in Australia. But nonetheless, it still causes the most mortality. Still a disease predominantly of smokers, but we're seeing around 15 to 20% of patients with lung cancer are non-smokers. The incidence rate seems to have paralleled the changes in smoking over time, and I'll show you how that's affected the type of lung cancers that we've had. Tobacco smoke has actually fallen, and in terms of the numbers, you'll see the total population smoking is actually a lot less now than we realise. But nonetheless, passive smoking and other factors are still significant contributors to the development of lung cancer. Air pollution, asbestos to a lesser degree, and one that you may not be aware of is that a relative having a cancer in the lung in the family does pose an increased risk in the next generation. We have made inroads in survival. Our overall 5-year survival 10 years ago used to be 17%, now it's 27%. And that's considering the fact that screening has only just started in Australia for lung cancer, and most presentations with lung cancer are still symptomatic, i.e. patients come with the cancer declaring itself rather than incidental findings. In terms of the differences between people who've had smokers and non-smokers, on the left-hand side are the non-smoking lung cancers, on the right-hand side are the smoking lung cancers. 15 to 20%, as I said, are related to non-smoking. And other factors I didn't highlight there, but household air pollution, close cooking in small environments, thought to be a risk factor, particularly in the Asian populations. A large number of the non-smokers related cancers tend to be from Asia. Women in particular are more dominant than men, but it's not exclusive. Now, this was lung cancer back in 2001 when I first started. We had small cell, which was classically a smoking-related cancer, as well as squamous cell cancer, and then the non-small cell cancer on the right. And we had, in the blanket term there, chemotherapy. If you're lucky, you were well enough to get one line of therapy and possibly another. This was advanced cancer because most of our cancers in that era presented late and advanced. And this is now 2026. And so the first thing I say to a patient when they come in with lung cancer is not to think of it as one disease and to go back to that dismal era of prognosis of decades ago, and to think about it as what specific lung cancer we have. And even our worst prognosis cancer, small cell lung cancer now, has had great inroads in the last few years because of immunotherapy. But I'll be speaking mostly about the right-hand side, the adenocarcinoma group. And I've put in the red here the various different specific subgroups related to specific genetic mutations that are targetable by specific drugs. And so when you have lung cancer, the question is, where do you fit into this schema as to what specific therapy you have, and therefore what prognosis you might have and what your future looks like. So why have we achieved this success in lung cancer? It all comes down to understanding biology, the emphasis on research, the type of work that Kim's been doing, and this has been over 2 decades of research. Cancer per se is characterized by abnormal and uncontrolled growth, caused primarily by an aberrant genetic mutation, either from an inherited gene or an acquired gene. When in lung cancer, we tend to use the word oncogenic driver. That means a mutation that's driving the growth in a particularly strong and robust fashion over and above other factors. When we talk about personalized medicine, we are talking about directing therapy towards those drivers. But the problem in cancer, and why we cannot achieve success across all cancers, is what we call biologic diversity and tumour heterogeneity. That is, tumours are never exclusively driven by one particular mutation, but those that are tend to have a better prognosis. So we'll go back 20 years. This is when I started. This was the first trial I was involved with, the drug called gefitinib. It was a randomised controlled trial of chemotherapy plus or minus this drug and placebo. So ambitious and so confident was AstraZeneca in their drug that they ran a phase 1 trial, which is determined to work out what the dose is, in parallel with the phase 3 trial. They were so confident that we would see a difference. Sadly, the trial was negative. It failed to show an improvement in survival. But what was observed in that trial, there was a subgroup of patients that seemed to have a Lazarus-like effect. They had dramatic improvements in their symptoms and their quality of life and quite prolonged survival. And so what happened was that led groups in Boston, in North America, at Harvard, and Dana-Farber hospitals to go in and have a look at the EGFR mutations. EGFR was the target of this drug, but they didn't know at the time that mutations existed. So they'd started this concept of molecular technology and had a look at it, and they'd identified 2 key mutations that were specifically blocked by this drug. And those patients that had the Lazarus-like effect were the ones that had those particular mutations. Since that time, we've developed other mutations. Along in the red is ALK, is a very important one. We discovered in 2009 that if we gave people up front these targeted therapies, it was far more superior than chemotherapy. And along the way, we've seen other evolutions. So we've made a big inroad in the last 25 years. On the left, this is a pie chart of the different mutations that have been identified in lung cancer. This is 2020, so it's a little bit old, but it demonstrates the difference over the 2 decades from 1999. This is from Memorial Sloan Kettering, a hospital that we at North Shore have a research partnership with. On the left-hand side, we always knew about KRAS. KRAS you might hear about in the press this week because of a major breakthrough in pancreas cancer. In lung cancer, we knew it was prevalent in about 1/4 of patients. But Over the last 2 decades, we've discovered other genes, and I'll go through some of these specifically. EGFR, the gene I highlighted, the drug earlier blocked, occurs in about 16% of Caucasians, about up to 50% of Asian patients. KRAS is about 25%, and then a bunch of others. The green and the orange highlight the drugs to which we have against those particular mutations. This is from a paper one of our ex-registrars, now fellows in Singapore, wrote, Aaron Tan, and what it highlights is the different distribution of these mutations in Asian populations versus Australian. So the EGFR gene occurs in about 46 to 50% of patients in Asia, but only about 16 to 20% of patients in Caucasian populations. And in terms of genes for which we, cancers of the lung for which we don't have a particular target, you can see that incidence is lower in Asian populations than it is in Caucasian populations. Now this timeline shows you the different drugs according to the mutation on the left-hand side, and then the drugs as they've been developed and approved by the PBS in Australia. A little bit of an embarrassment of riches, but one that we're very happy to have. And you can see across the right, on the right-hand side, you'll see early disease in one of the boxes. So in some of these situations, we've been able to transfer the advances in advanced disease into early stage cancer, and in those patients, obviously, hope for cure. Many of these patients with these mutations are what we call chronic disease patients, living with their cancers. Some now over a decade with advanced disease, some even with brain metastases still alive. So how do we get to this point of how do we identify these patients? Until November 2023, in Australia, it was done by piecemeal testing, individual gene testing. And at that stage, we looked for EGFR because that was the one that was first known. Then it was ALK, and then another one called ROS1. Around 2023, the technology was becoming more accessible and a little bit cheaper. So we started to do small gene panels. NGS refers to next generation sequencing. I'll show you a chart on the coming slide what that means. As of November 1st, 2023, the government approved upfront reflex testing for newly diagnosed patients with lung cancer. So if you had lung cancer, you'd be getting the panel to test for these genes. Why? Because there were drugs available for those genes. Often it is the fact that there's a drug or a therapy available that drives the change. Now, this is the difference between next-generation sequencing and single-gene sequencing. If you think of it, a very potent lure, single gene, you're looking for one gene. Next-generation sequencing, you're casting a wider net, but you're likely to find more things in that net. Next-generation sequencing is a platform. It refers to technology that is able to look at multiple genes, and they're usually using some form of machine technology. And it's changed a lot in the last few years. Now, another word I want to bring up with you today is called comprehensive genomic profiling. That means not just looking for a small panel of genes, but looking either across the whole genome, that's whole genomic profiling, or exome sequencing, or a substantial number of genes. And we have platforms that could look for 150 to 300 to 500 genes. Now, you might think that's great, we can see a lot. It's only as good as what you can do with the results. But if you don't look, you don't find. And some of the things we've learned over time is what is the value of that broader knowledge in patients with the mutations. And I'll show you a case example at the end that highlights that. Why would you not do this broad test? Because it's more expensive, it takes more time, there are technical issues, you need more tissue for it. And then at the end of the day, you may get a result, but what are you going to do with it if you don't have a drug to do it with? So I thought I'd draw attention to some of the things we've done in the Australian landscape across Australia, that's issues of scale, what we've done not at a local level but at a national level. This is a study I co-led with a colleague from Peter McCallum. We were funded as a collaboration between industry, government, and academia. We received a $5 million MRWF grant that Roche pitched in similar amount for, and we ran the trial through the NHMRC CTC, and Omico is a group that you may be familiar with that does genomic testing on tissue in Australia. What we did is we wanted to set up a platform across the whole of Australia for all newly diagnosed lung cancer patients to have the genetic testing done so that we have information that could guide our therapy. The purpose was to compare it with standard of care, which at the beginning was those 3 genes I told you about, but which over the journey of the trial changed into a small gene panel. We arbitrarily chose 1,000 patients. We thought that was big enough to see a few results. And this is over here, the chart of Australia shows you where around Australia patients were able to get testing done. And you can see Darwin there, some remote places in Western Australia as well. And that platform is the thing I want to show you today. It's not just the learning about the cancer, because at the end of the day, lung cancer is different to brain cancer. But it's scaling things around nationally and giving access and equity to patients across Australia to the best technology. So we did the testing, and then our goal was to try to look for therapies for patients, some of which were available in the PBS, some of which were available on sponsored trials, commercially sponsored trials, and some of which were available in sub-studies. This is a more complex diagram highlighting that distribution of where we would recommend the patient go. We also expected that the CGP would identify more mutations than the standard of care, and I'll show you our results on the coming slides. One of the things we were quite proud of was we started this project just before COVID, and we finished in a timely fashion. That's actually what's called an accrual curve. You estimate you're going to recruit 1,000 patients in a given time, and you can see we actually matched that despite the challenges of COVID. And the reason we did is largely from remote referral. So we had 16 sites across Australia in the different states, but we also allowed any oncologist anywhere in Australia to go online, put their patient's details in. The patient was then contacted to consent over the phone, and they were able to get their tissue sent from the lab to the major centre to get tested. And this just shows you the distribution of number of patients. So two-thirds, about 60% were by participating sites and about 40% were by remote referral. This demonstrates the enrolment by sites, largely based around population, but it shows you that patients all around Australia, including Tasmania and Northern Territory, had access to this technology. This shows you the disposition of the patients. Of the 1,000 patients who consented, some didn't have were not available by standard of care. We were able to complete the test successfully in 83% of patients. Some of the failures here we learnt a little bit about. That was quality assurance to do with the tissue extraction, the technology, for example. And you can work on these things here. And of those who had the completion of the genomic profiling, the detection of an actionable genomic alteration means one of which you could actually recommend a drug specifically for was around 50%. This was the distribution, the pie chart that we had in these patients. So around 50% of patients had an actionable mutation for which they could be sent down the pathway of a selected therapy. What was the access time for this result? 29 days, which is a bit slow to our liking. A large part of that time was absorbed in getting the tissue from where it was biopsied to the actual lab. That's something that we need to work on. The lab itself was quite good. The lab could do the assay within 7 days, but it was actually getting the result there that was the hard part. And around 23% of patients needed to have an additional biopsy. And we learnt a lot if you have a lung cancer patient now, we know what type of biopsy you should have. Now this pie chart shows you, what I want to highlight here is standard of care was grey and blue was what came from the result. And if you have a look at the common genes, you can see blue is bigger than grey, meaning we did find more genomic alterations. And of those who had a genomic alteration, in the orange are the ones who went on to get a targeted therapy. By applying this technology, we found an additional mutation in 13% of patients, so it's 130 across the board, leading to a 45% increase in targeted therapy across. If you look at the survival, those patients who went on to get targeted therapy had the best survival. That's the curve on the top. Those who received standard therapies, chemotherapies in the middle, and of course those who had no treatments, smaller group at the bottom. Across the journey of the patients, the practice changed. So we weren't just doing those 3 genes, we were doing those small gene panels. One of our goals was to do a health economic analysis to try to convince the government it is worth funding this upfront for whole gene profiling. They have approved a small gene panel. We're still waiting to do this analysis because if those 13% of patients led to 45% extra treatments and the survival impact that we show is if we can demonstrate that that's economically valuable, then we have a good argument now to say we should be doing upfront whole gene profiling in lung cancer patients. We're waiting to do that. I just wanted to acknowledge the team. This is a huge team effort across Australia. These are not everyone represented. On the left was the research team, on the right is the participating centres. I'll move on to liquid biopsy. I'm going to focus primarily on circulating tumour DNA, circulating free DNA, but you'll hear more about the diversity of what liquid biopsy is from Kim. In lung cancer, we are still exploring those other technologies, but our large research effort in the last few years is focused around circulating DNA and DNA fragments. So just for nomenclature, circulating free DNA refers to extracellular DNA found in the blood, thought to be arising from a tumour. Circulating tumour DNA is that component of cell-free DNA that we think originates from a tumour as opposed to normal tissue. And the value of a liquid over tissue is that it's easy to get a hold of. You can just take a blood sample. You can repeat it multiple times. Tissue, as you know, is not always easy, particularly in brain cancer patients, which you know more than anything. Now, this is just to highlight the fact that up to 20% of patients with tissue biopsies often have inadequate tissue for genomic profiling. The other advantage of liquid biopsies, it tells us a little bit about the overall impact or genomic impact of on the patient. So you have a patient on the left who has a brain metastasis, a liver metastasis, and a primary. When you collect their blood, you could potentially be measuring fragments from any or all of those particular sites of metastases, and thus getting a better view of the whole nature of that cancer rather than a specific site. This is not a replacement for tissue biopsy. I'll show you an example where we did do a tissue biopsy on a patient, and it was quite valuable. And also, as you go along, if you treat a patient in B is called temporal heterogeneity. If you have a patient and then you treat them with a treatment, you alter the nature and constituency of those cells as you kill off some of the cells and allow others to mutate and develop. And so by repeating in the blood the DNA or in tissue biopsy, you understand what the transformation has been in the patient when the tumour is no longer responding. The other phrase I want to draw your attention to is called MRD, which refers to molecular residual disease or minimum residual disease, as we often call it. People with hematologic malignancies have been using this for some time to see whether the leukemia is in complete remission and gone. In solid tumours, it's only a more recent technology. And it's really, again, looking at fragments of DNA as measurable in the blood. But the sensitivity has to be better. If you have a patient whose tumour's cut out and you're doing an MRD assay, you're looking for very tiny fragments, 1 in 10,000, even higher, to see if you can detect the presence there. I'll show you some data that shows it's a very powerful prognostic tool, and it can help guide decision-making as to whether someone should have chemo after surgery or they could be left alone. So these are the applications of some of this technology in lung cancer. In diagnosis on the left, on the bottom left-hand side, you can use it to escalate therapy. If the DNA is still persistent in the blood after treatment, you need to add more therapy to see if you can get rid of it. If it's gone away, maybe you can take away some of the toxic therapy and give less therapy. On the right-hand side up at the top, in the patients who've had surgery and had the tumours cut out, you can do this MRD assay. If it's positive in the blood, you know that those patients should have something to try to reduce recurrence risk. And in the bottom, and this may be perhaps more accessible, more applicable in terms of the principle in patients with brain tumours, these are patients with lung cancer who've had chemoradiotherapy, who have persistent changes on a PET scan. You don't know whether it's viable cancer or not. Circulating tumour DNA here is often useful in determining whether it's radiotherapy-related changes or it's actually dead tissue. Now, this is a Canadian study that did upfront blood tests as well as tissue biopsies. They found 20% more patients with biomarkers detected if they did it concurrently. They also found the turnaround time was 9 days versus 15 days, so you can get a result faster. This study that Adrian and I and others at North Shore participated in, so it's the Memorial Sloan Kettering group, did a study of circulating tumour DNA in lung cancer. We found that those who had a positive oncogene in the blood did better. We know it's a prognostic sign. Can you get better therapy? We also know that if you were to able to have your treatment selected by that DNA, you got a better result in terms of survival. This somewhat complex diagram is just to show you the diversity of causes of resistance if you have a particular mutation. This example is about EGFR. The resistance could be in the EGFR gene, could be in other tracks developing, or on the right with other various mechanisms. You can detect this in the blood and therefore tailor therapy to patients as you go along. This is 6 curves from 6 trials in lung cancer that looked at the presence of detectable DNA in patients who had their tumour cut out. And in all cases, quite consistently, the bottom curve means the survival is not as good as the top curve. In all patients, in all situations, patients who had a positive MRD did worse than those who didn't. This is a particular result in the EGFR population. This is an oncogene targeted gene. So in this study, again, patients had a targeted therapy for 3 years after their cancer was cut out, and those who did get a better survival. Then they measured their blood every 3 months for the whole 3 years and found 8% of people had detectable DNA in their blood. And those who did, around 5 months later, developed metastases or recurrence in their CT scans. And that led to this trial. Now, what we're doing in this trial, this is still going, is we're taking the same population of patients, we're measuring the DNA in their blood, and if it's present at the end of the resection of the primary tumour, we're going to give chemotherapy in addition to the targeted therapy, because we know from the previous study that targeted therapy alone wasn't completely successful. So there's a variety of applications of this technology in lung cancer across the course of the disease. One of the applications is in patients who have advanced disease in determining whether their treatment is responding before it's evident on a CT, and also in determining if their treatment will fail before that's evident on a CT. And intervening before that happens, we know, can alter survival, and has recently been shown in a study in breast cancer. So this is my case example. This is a real patient, a 73-year-old GP who retired. Actually, used to refer me patients before he retired. He's of Asian extraction, and he had discovered that he had this EGFR exon 21 gene. He's a non-smoker. This is a non-smoking related cancer. And unfortunately, his disease had bone metastases and he was diagnosed. So he was put on targeted therapy, which is called osimertinib, which served him well in remission for 8 months, and then his bone metastases started to progress. Standard of care at the time was to give chemotherapy, which we did, and he had an excellent response. And the gene persisted when we measured it in the blood. However, another 8 months later, he started to get progression within the liver, and so I biopsied that, and I found another mutation, which is called NTRK, for which there is a targeted therapy available. I measured his DNA at various time points and was able to demonstrate before he showed evidence of improvement on a CT that he was getting better, and also that it was failing. This is just an example of the kind of reports that we get. And one of the things I want to emphasize here is the value of what's called a molecular tumor board. You don't just do these results and get a printout off a machine. You actually need a team of people to interpret and collate the results. So this was this patient's journey. Starting on the left, he didn't live as long as we would have expected for this particular condition, but he did live longer than he would have expected because we're able to apply this technology and intervene and give him treatment along the way. So that's led to this trial. We were successful through the Thoracic Oncology Group on a $15 million grant to look for applying this technology throughout the patient journey. Most of the times when we get approval through government to do a test, it's one-off. You do it once, that's it, you're never going to get it again. What we're trying to test here is the ability to apply this test along the whole patient journey. If the patient's tumour is growing, we do it again. We put them on a new treatment, we measure it again, see what happens. If it grows again, we do it again, we keep going. What the information we get, again, we'll try to funnel patients into specific therapies, as you can see there. We've modelled it around our expectations based on prior experience as to what we hope we'll see. This is the team, multidisciplinary team across Australia and multiple sectors, including health economics and laboratory and molecular pathologists and clinicians. So, in summary, lung cancer has been identified to have multiple molecular targets, which highlights the importance in lung cancer of genomic profiling at diagnosis. But no, this is not the only tumour type for which molecular targets exist. And if you're a patient who has one of these targets, this could have big impact for you. The Aspiration trial demonstrated that we can scale this nationally across the country, and we can do it in a way that wherever you are, you can have the technology accessible to you. Blood for circulating tumour DNA, I've shown you can complement the information you get from tissue, both in diagnostic, in monitoring your response to therapy, in identifying reasons for resistance and therefore changing or adapting therapy, and in monitoring after surgery whether you're at risk of recurrence. Our Aspiration 2 trial is evaluating ctDNA at a national level across the whole patient journey, not at one point. So what's this got to do with brain cancers? I thought I'd finish off here. Clearly, brain cancer is not lung cancer, and I know that only too well. Genomic profiling, I will say, not just in relevance to brain cancers, but in any cancers, is only as good as what you find and how that particular abnormality drives the mutation, whether you have a drug access to it and whether that access gets into the brain. Many mutations we find are not targetable. So there's still a strong place for chemotherapy, radiotherapy and immunotherapy. Up to 70% of patients with particular lung cancers have brain metastases, and it's often a cause of death, escape in the brain, with a condition we call leptomeningeal disease, which is a very nasty form of brain progression. But we know from lung cancer that many of these drugs can enter the brain with high effectiveness. What we aren't able to do very well in lung cancer through circulating tumour DNA, and perhaps this is what we'll learn about technology that Kim's looking at, is what are the reasons for failure in the brain? Circulating tumour DNA is not a very good test for that. Partly because of what's called the blood-brain barrier that you'll hear more about, also partly because in solid tumours, when you have tumours in the systemic circulation, you get far better release into the systemic circulation. But we do have new technologies. These MRD assays are ultra-sensitive, very low, small detection fragments. So I guess that's principle of detection of small fragments in the blood that can be released from the brain may still be valuable in brain tumours. And I guess I'll leave it on that note and pass on to Kim. Thank you.
Thank you very much, Nick, for that very inspiring talk. We'll hold questions to the end. We now welcome our second speaker, Associate Professor Kimberley Alexander. Professor Alexander is a biomedical scientist and Director of Brain Cancer Research at the Chris O'Brien Lifehouse. She co-leads the Sydney Brain Tumour Program and has established one of the most comprehensive brain cancer biobanks in Australia. Her research is fundamental in finding new ways to detect, diagnose and monitor brain cancers. Please join me in welcoming Kim to the stage.
Excellent. Hi, everyone. I'd like to thank the Brain Cancer Group for inviting me to speak with you this evening. It's a great honour to be here at Parliament House. So tonight I want to talk about why brain cancer remains such a difficult disease to manage, how the Sydney Brain Tumour Bank is helping researchers ask better questions, and how liquid biopsy approaches, also using liquid biopsy, may help us track brain cancer biology more safely and more effectively over time. So brain cancer, like lung cancer, is not a single disease, but there are about more than 120 different subtypes, and these are just brain cancers that start in the brain. Even within a single tumour, there can be remarkable diversity. Different regions of the same tumour may behave differently, evolve differently over time, and respond differently to treatment. The brain is also a really difficult organ to access, so surgery is often essential, but neurosurgeons must constantly balance removing as much tumour tissue as possible with preserving the functions that make us who we are, like our speech, our movement, our memory, our personality, and independence. Many therapies, as Nick mentioned, also struggle to actually reach tumours effectively because of the blood-brain barrier, and this is the brain's natural protective shield. But brain cancer isn't just difficult to treat, it's also difficult to monitor accurately as the disease changes over time. To better understand how brain tumours evolve, why treatments fail, and how we can develop better diagnostics and therapies, we need access to high-quality patient samples. So biobanks are one of the most important tools we have in advancing brain cancer research. And a biobank is much more than just a freezer full of tissues. Its real value comes from linking patient samples to the clinical story that surrounds each person. So a tumour sample on its own can only really tell us so much, but when it's linked to imaging, molecular testing, including next-generation sequencing, treatment information, and survival outcomes, it becomes far more powerful. And that's what makes modern biobanks so important. They allow researchers to better understand the tumour biology, discover new biomarkers, develop more personalised therapies, and also improve access to clinical trials. Now, these resources are also becoming increasingly important in the new realm of AI, artificial intelligence-driven research, because reliable AI depends on large amounts of high-quality patient data. So increasingly, biobanks are becoming essential to the future of precision medicine in brain cancer. At the centre of our work is the Sydney Brain Tumour Bank, which is a resource built from patient donations. And over the years, about 10 years now, it's grown into one of Australia's largest and most comprehensive brain tumour banks. We now have samples, patients, about more than 1,300 participants consented, which is pretty good for a rare cancer. And we've collected material from more than 1,850 neurosurgeries. I co-lead this resource with Dr. Lavanya Sakwadasilan, who is a neuropathologist and a molecular pathologist as well. And her expertise in brain tumour diagnostics, because there's so many different subtypes, is really central to how we classify and understand tumours. We collect a wide range of patient samples along with really rich clinical information. And it is the richness of this data collection that changes the kinds of questions that we can help answer, or ask, sorry. So not just what does this tumour look like and how does it grow in the lab, but how does the biology that we're seeing relate to what actually happened or is happening to that patient. And that's really important if we want research to be clinically useful and not just scientifically interesting. So samples and data collected here in Sydney are now supporting studies locally, nationally and internationally. One of the most powerful aspects of a biobank is that a single donation can continue to contribute to research for many, many years to come. So a sample doesn't just support one experiment in one lab at one hospital. It becomes part of a much broader collaborative effort to improve brain tumour diagnosis, treatment and care. So one example I want to draw on is that there's a number of researchers across the US, Europe and China who are using MRI scans and digitised images of tumour tissues under the microscope. And they're using these resources to build AI models, and these models can are learning how to predict what that tumour type is, how it's likely to behave, and also which treatments may be the most effective. But these AI technologies can't simply be imported from overseas and assumed to work here. They need to be tested and validated on Australian patient data within Australian healthcare systems. And that's another reason why resources like the Sydney Brain Tumour Bank are so important. Not only do they support new research ideas and directions, they also allow us to assess new diagnostic approaches in ways that are directly relevant to our own patients and clinical practice. So many of you in this room will know about glioblastoma, which of course is the most common and aggressive malignant brain tumour in adults. Despite advances in our understanding of glioblastoma over the last decade, really, it does remain one of the most difficult cancers to manage. One of the major challenges is that we're still really heavily reliant on surgery. Now, surgery is critically important because it allows us to actually diagnose the tumour tissues, and it is an essential part of treatment to remove, to help the tumour burden. But brain surgery is, of course, highly invasive and can't always be repeated safely. Because glioblastoma tumour cells infiltrate widely through the brain, even if a scan suggests that the tumour has been completely removed, microscopic tumour cells are often left behind. And even after the standard chemotherapy and radiation therapy protocols, these tumours, glioblastomas, almost always reoccur. So monitoring the disease during and after treatment is also another major challenge. MRI scans are essential, but they don't always provide clear answers. Sometimes brain changes seen on a scan are actually caused by treatment effects rather than the tumour growth. And this uncertainty can be incredibly stressful for patients and also very difficult for clinicians trying to make the best decision about treatment for their patients. Another problem, there seems to be a lot of problems, sorry, that I'm listing, is timing. By the time tumour progression becomes clearly visible on imaging, the biology of the tumour may already have changed significantly. This is where liquid biopsies become particularly exciting. Instead of relying on imaging or invasive surgery, liquid biopsy looks for tumour-related signals circulating in the blood. Now, because blood samples can be collected safely and repeatedly, they offer a possibility of tracking disease changes throughout treatment and follow-up, and may actually help clinicians understand if MRI findings are uncertain. A major challenge for developing liquid biopsies in the for brain cancer patients, though, is again the blood-brain barrier. So this protective barrier that stops a lot of treatments coming in also stops genetic material being released into the bloodstream. So the strategies that are used by other cancer streams, including lung cancer, aren't so effective here. But us and other groups have identified a really rich source of brain tumour molecules in the blood, packaged in tiny particles called extracellular vesicles. And here you're actually looking at them, EVs. They're being measured in real time, and each of these little twinkling dots represents an individual EV particle moving through the measurement field. Now, brain tumour cells constantly release EVs into the bloodstream, and these EVs carry a rich cargo of molecules, including proteins, RNA, DNA fragments, lipids, and other biological signals. They're easily captured from body fluids, and our team has developed methods to measure thousands of molecules carried inside these tiny particles. So what makes these really interesting for brain cancer research is that EVs give us a possible window into what's happening in the brain tumour without needing surgery to access the tissues. So this slide describes an approach developed in my lab that we call blood fingerprinting. From a small blood sample, around 1 millilitre, we isolate EVs and measure thousands of molecules inside. Rather than searching for a single marker or a panel of markers, we use AI maths to look for broader molecular patterns. And that's what we call a blood fingerprint. Using this approach, we've found that glioblastoma, other brain tumours, as well as tumours that have spread to the brain from other parts of the body, each have distinct blood fingerprints. In other words, there appears to be enough biological material in the blood to distinguish different brain tumours before surgery. And this we find particularly exciting because it suggests that in some cases we may eventually be able to make treatment decisions without needing surgery or before surgery. We've also identified blood fingerprints that can detect a GBM recurrence with about 93% accuracy. And so currently we've got some funding to run some larger validation studies using around blood samples collected from around 350 GBM patients in the Sydney Brain Tumour Bank. Those bloods were collected at multiple time points, like Nick described, as well as blood samples that were captured during the VER2 clinical trial. But more recently, I've become very interested in urine, which has alarmed some of my family, friends and neighbours, many of whom have been asked and consented, of course, to contribute their morning samples in the name of scientific research. Now, this might sound a bit surprising at first because brain tumours are clearly nowhere near, not located anywhere near the urinary system. But if you think about how strong the signal we're seeing in EVs from the blood, and that the urine is the major clearance route of EVs from the body, it might not seem so crazy after all. Urine collection is also very attractive for liquid biopsies, as the collection process is, as you all know, very simple, safe, and for some people very frequent. We call this concept the liquid gold biopsy, which I think works on a few levels. And we've, from several hundred patients, or several hundred samples, we've captured EVs from a library of urine that we've stored in the Sydney Brain Tumour Bank and used our methods to profile the molecules inside. So we found distinct signals in urine EVs from patients with GBM. And this, comfortingly, includes some of the same markers that we see in our blood tests. In particular, we've detected a dramatic increase in lipids, or more specifically triglycerides, in patients' urinary EVs. And I think these promising results provide a strong rationale to continue our liquid gold journey. And we're currently confirming these findings in large patient groups, including patients with kidney and prostate cancer. We thought that was a good place to start, cancers that are much closer to the urinary system. And we're looking to see if our findings are specific to brain cancer, or if they also detect other cancers too. So while some people think that the urine is just biological waste, I believe it is liquid gold and carries a surprisingly rich amount of information that we can use to learn more about a person's brain cancer and potentially track them closely over time. Now, I did use AI to generate this figure, and I fed it into it a photograph of the postdoc that works with me, Dr. Susanna Halal, and the only thing it really preserved about her is her gorgeous curly hair, but unfortunately it doesn't look very much like her. We're also thinking carefully about how our discoveries could eventually become practical tests that doctors can use in everyday clinical care. We're working with some brilliant engineers at Sydney University to build these testing devices to our specification. One of the technologies that we're exploring is called microfluidics, and this is sometimes described as a lab-on-a-chip test. And these devices essentially have tiny channels where the patient's urine is passed through, and we're actually using sound waves to separate out and capture different size particles. And what's really cool is once those EVs are separated out on the chip, we can then measure tumour markers on the chip itself. So conceptually, it's a bit like a rapid COVID or pregnancy test, but designed to detect molecular signals linked to glioblastomas. So if these liquid biopsies prove successful, they could provide a simpler, safer and more accurate way to monitor brain tumours, and may also help connect patients with clinical trials and emerging therapies sooner. And I really hope that one day we see as many drug options for glioblastoma as there are for lung cancer. One of the major advantages is the potential to detect tumour activity before it becomes visible on an MRI, or before clinical symptoms, before the patient starts to deteriorate. Helping clinicians also interpret those uncertain imaging findings, particularly when it's difficult to distinguish tumour progression from treatment effects, and of course support therapeutic decisions that result in the best possible outcome for patients. There's also a very human side to this. Repeated scans and waiting for those results can be incredibly stressful for patients and their families, something that people refer to as scanxiety. So we're hoping that these approaches can also reduce that sort of uncertainty. We also think that this might actually also help with access to care, because blood and urine can be collected anywhere, really. We think that patients living regionally or in rural settings, could actually just have their sample collected close to home and sent to a central specialised sort of testing area. But I want to wrap up with my talk with just a few take-home messages. First, generous patient donations power discovery. The Sydney Brain Tumour Bank exists because patients and families generously donate samples and information, often at incredibly difficult moments. Second, liquid biopsy adds biology to the scan. EVs from blood and urine may help us monitor disease more safely, more accurately, and more frequently. Third, the goal is clearer decisions, better monitoring, better treatment, selection, more personalised care. Now, the liquid biopsy stuff is not meant to replace anything. MRI, surgery, pathology is all essential. Really, this is an extra layer of information that clinicians can hopefully use to support those important decisions. And lastly, I think maybe many of you are aware that that medical research in this country is drastically underfunded. The main grant category in our funding cycle has applications have about 8% success. So really in this area we do need more funding, particularly for rare cancers like brain cancer, because patient donations, they actually allow the research to be possible, but sustainable funding actually brings us better tools, better treatments and better outcomes for patients. Thank you for listening.
Thank you so much, Kim, for that fantastic talk. Thank you, Dr. Holland. Now, to close, I would now like to introduce a stranger, or rather a familiar face, to our audience. Professor Michael Back is Senior Radiation Oncologist at Royal North Shore Hospital, known to most of you, and undoubtedly our guru in brain cancer radiation oncology. He will be presenting the closing remarks and closing out the evening.
Thank you, Adrian. And on behalf of the board of the Brain Cancer Group, I'd like to thank people for attending this evening as well. And importantly, just putting another note out there for advocacy and the importance of this illness, which may have been neglected over many years, but we're trying to learn those patterns. We're trying to work out those things. Adrian and Kim are Nick and Kim have given some really good examples of how things can change over time with observation, with understanding, and interpreting things from our research. I'll make a couple of comments. I was fortunate enough to work in Singapore between 2001 and 2007, and I was part of that, seeing that Lazarus effect. It was bizarre. I came from Newcastle in New South Wales, obviously, where people, and I was managing people with lung cancer, and it was a heavy smoking related illness, and people obviously around that area also working in mining industries, etc. And unfortunately lung cancer was one illness, or as Nick described, two illnesses, one looking completely different under the microscope compared to the other one, but that other one was just one disease, and it was managed as one illness. I went over to Singapore, and also we managed it as one illness, but we put people onto that trial, and that trial was a negative trial. It failed, but the Asian investigators all looked around each other and said, why are our patients still alive? And our patients had brain tumours or brain metastases, and they were still alive. And that's when the company was about to close, and the FDA in the US was going to remove the registration of that drug. And we said, no, you can't close that because we're seeing our patients alive. And it made a huge difference. So although there was only 10% of people around the world that had that mutation, in the Asian countries, it was huge. And we saw that difference. And it came from an observation of patterns. And it came from understanding not the main endpoint from the clinical trial, but looking at the subgroups within the clinical trial and gathering more of that information. And I remember being completely surprised at that time, and I thought that, well, this is a little bit of a panacea, it's going to work for other illnesses. It hasn't flowed onto our patients with glioblastoma completely yet, but in 2010 we learned about the IDH mutation, and that was one step. Nick's slide showed that we've got in lung cancer, another 8 or 9 mutations from there. And that's where we have to learn. And that's not going to come from a simple laboratory test. It's going to come from looking at patterns and looking at patterns of the way the brain tumours act. In our research at the Brain Cancer Group, we're looking at the imaging pathways and looking how that alters between patients and trying to find those patterns. And then in Kim's example was also good. When another patient who I was involved with back in 2016, she was a lady, I think, in her mid-30s, and she had approximately 25 metastases in her brain, multiple small lesions, and she had one of those mutations that Nick described. And in days gone by, I would have managed her with whole brain radiotherapy, but we realised this is different, and we watched it. But I still remember it because it sticks in my head. In June 2016, her scan started to change. It got worse. And I remember saying to Nick, we're in trouble here. We might have to use whole brain radiotherapy, which we didn't particularly want to use on this lady who was a scientist and who was essentially asymptomatic. And Nick said, let's remove one of the lesions. I said, what? And there was no symptoms from the brain lesions. They were all asymptomatic, but one particular one was changing. And Nick said, let's learn from that one, and removed it. There was a subtle change in the mutation, a different drug therapy. I no longer see that lady, except I run into her in the waiting room at Nick's clinic, and I look up her brain scan, and I'm thinking, it's 2016, it's 2026, and she was facing whole brain radiotherapy then, and she doesn't even see me now, and we haven't treated her. It's a great example of where we've come by learning the lessons along the way, being attentive to the subtle changes. Now, we've got a long way to go to glioblastoma. But what we are learning is trying to get the collaboration. So within the Brain Cancer Group, we do a number of collaborations. That slide that Kim showed with all the different countries and the research links, that's fantastic work. We set up our data bank, but we sort of modelled it on Kim's data bank, just getting the information, so that if we have to explore a particular question, our databank can potentially talk to Kim's databank, and therefore we get some sort of collaboration. We're adding other things on in terms of imaging and other clinical factors. So if Kim's got a suggestion from her data, she can talk to our data, and we can extend down that imaging route or into the other aspects that we're collecting. So it comes through that collaboration. I think that's one of the great and most important things. We only have about 400 odd patients with a high-grade brain tumour being diagnosed in New South Wales every year, or ones which are probably classified up towards a glioblastoma. That's too many, but there's not a lot of information there, and we have to get that information from our patients and communicate that between the different centres. So we've got Mark Hughes Foundation here today, and Mike Fay's doing good work up in the Hunter region with his laboratory. We've got the Central Sydney campus being the recipient of the federal government $6 million grant to set up a research centre, but not just a research centre in one campus, but one that communicates between different centres and collaborates. We've now set up the Australian Brain Tumour Collaborative, which is a Australia-wide collaboration of all the different not-for-profits in brain tumour management. So as we try to identify streams of interest that we can potentially share, but also identify and be advocates on a national basis to the federal government, and that's already working, and Mike is part of that with the Mark Hughes Foundation, as with another 16 not-for-profits between adult and paediatric primary brain tumours. So I think in this sort of community, we're trying to pool our resources, collaborate, and I'm pleased to see that our ideals that we try to set up when we changed our name from the Sydney Neuro-Oncology Group to the Brain Cancer Group are sort of coming through that, because we're trying to get that collaboration. And that's part of the theme today, like trying to learn from what other people do to try to push forward our endpoints and try and do better for our patients. We don't have anywhere near the answers, and it's pretty obvious. But we are getting improvements. We're seeing people living longer. We're seeing people living better. And hopefully we will get that push, as we've seen with lung cancer, from a condition which was absolutely horrific to one which is not fantastic, but it's one which we're seeing now people who are getting long survival cures and who are leading good lives subsequent to their therapy. Now, it comes, as Kim mentioned in her talk, from the awareness and the contributions from our patients. Every person's scan, I think, should be used to get a better understanding of how people's brain tumours act. So every bit of information we try to gather, and we're trying to put that into a way that where we can not only understand that, but share that experience, and so that all of our patients are contributing to it. And for the people who have supported us financially as a not-for-profit, those initiatives, that collaboration is what we're trying to do. And we've come a long way over a number of years. I think we're getting a really good foundation, and hopefully we can push forward with government, both federal and state, to try to make those endpoints of trying to reduce the burden of this illness on our society so much less of a burden, and also try to push further, as we've seen with lung cancer, to where we're getting cohorts of people who are living for longer periods of time and reaching cures when we didn't expect them to be. So I thank you again for your awareness, your advocacy, for being part of this tonight. And I hope that we can continue to meet at this Parliament House session once a year. I think it's a very good place to put our flag in the ground, and to also remind our government of the importance of looking after people with brain tumours. Thank you.
Thank you very much, Michael. Last message, because I'm mindful State of Origin is about to start in 10 minutes. The Brain Cancer Group is dependent on community support to maintain our research, education and patient support programs. So you might have noticed in the foyer, we've got a small store. So if you can donate or buy some of our merchandise, that will be greatly appreciated. Last but not least, I want to thank Dennis, our IT AV guru, who has helped Suzanne put together this event together tonight. Much appreciated, Dennis, Suzanne, and Tracy, always. Indeed. So now we do, if anyone has any urgent questions, we do have some roving mics. If not, the speakers may be at the foyer afterwards as well, if you're a bit shy and just want to go up to them directly. Clearly, we have not planted any questions in the audience. We'll just wait for the mic, because we need to capture the audio.
Thanks very much. Just a little bit of background. My wife died 5 years ago and Michael Back was one, and Helen Wheeler looked after her. But that, having been coming to these sessions for over 5 years and talking to different people, we always come up with we're short of funding. Now, there is a great opportunity. If you look at just recently, everybody knows about the work the former cricketer used his wife's death to really drive money in and do great work on breast cancer. Neil Danaher died the other day, and he raised $100 million for MMD. So those people use their positions to increase funding. Now, there's a great opportunity at the moment, obviously, sadly. Another famous AFL player, Jonathan Brown, who won 3 premierships for the Brisbane Lions, has been diagnosed with brain cancer and has had an operation. I don't know him, but I just have read about it. If somebody from here can approach him and use that opportunity, he might come forward and help raise the profile and therefore the money. So that's my suggestion to you. Somebody from here get in contact with Jonathan Brown and his family so you can really increase the funding to deal with this terrible disease.
Thank you. Kim?
Thank you. Yeah, that's an excellent point. I'm very, very sorry to hear about your wife.
Yeah, thank you. Also,
something-
Neil Danaher was first cousin of
Something
Helen.
I unfortunately neglected to mention at the conclusion of my talk is that there are wonderful foundations, and we receive wonderful philanthropy support for our work, including the Mark Hughes Foundation. And Mark Hughes, of course, is a well-known footballer. Also from Cure Brain Cancer Foundation and the Brain Cancer Group as well. I think there are a number of fantastic foundations and philanthropy. I know today, on the weekend, there's a fun run for Richard Scollier up in Brisbane at a pathology conference. So I hear you, and it's a very, very good suggestion. And I think any opportunity we can to raise more awareness and more funds, I know we're going for it. But that said, we still need some better government funding, more sustainable funding, not just to fund projects, but also to fund scientists to stay in the field and continue the work. But I get your point, and thank you for it.
Indeed. All right, if there's no more questions or comments, I want to thank everyone again for your attendance tonight. Thank you for your support, your annual support in coming to Parliament House to join us to raise awareness for brain cancer. We look forward to meeting you again next year, so about the same time, hopefully not on State of Origin Game 1. Thank you so much and have a good night.